Thank you for joining Once Changing the World. I'm your host, Eddie Avil, and today we have with us Vidita Vaidya, a neuroscientist and professor at the Tata Institute of Fundamental Research, Mumbai. Her primary research areas are neuroscience and molecular psychiatry. Her pioneering research explores how psychedelics can reshape mental health treatment, offering new hope for those battling schizophrenia, depression, and anxiety. Professor, really appreciate you taking time and being part of the podcast. Wanted to directly jump into the brain, because I've had some conversations with AI scientists and researchers, and whenever I kind of probe deeper into, these, how do these models actually work? These large language models. The answer which I normally get is that, we don't really know because it's still a black box. The brain also seems to be like one of that, because whenever I've had spoken to a couple of neuroscientists, researchers, but that's what I largely get, that it's still a black box. The brain. How cool is that? 80 billion neurons, 100 trillion synapses. The way they fire and wire, they bring all our senses: sight, sound, touch, smell, taste. How much do we actually know about the brain? What is it doing?
Pretty decent understanding of how the individual building blocks work. So we have a good understanding of how neurons fire, how they respond to signal, how they produce their responses, how they work in terms of their connections with each other. Part of the problem is when we start moving out of looking at very simple, perhaps more simple behaviors, which would be something like, let's take a worm, because a worm we've mapped every neuron and we know everything that those neurons are connected to. So we've mapped all the synapses, we know every neuron that there is, and then we can study a behavior like turning or escape behavior, etc. For those, we have still a reasonably decent understanding of the building blocks and how they produce the behavior. The minute it gets into complexity is when you move to higher organisms which have millions of neurons, and they're coordinating activities across multiple locations to eventually give you a behavior which is an emergent property of these networks talking to each other. Now, because they have the networks are already complex and there are multiple nodes interacting with each other to eventually give you a behavior, it becomes very hard to pin it down in the preciseness of precisely these neurons produce precise behavior. We're still not doing too badly in that in rats and mice, we still have a reasonably decent understanding, but it depends on the behavior you're looking at. The more complex and the more, broad a behavior. For example, if you tell me, can you give me the circuit in the brain that produces conscious states? It's going to be hard to pull that off. Or even if you say, give me a network in the brain that is associated with laughter, which is a fairly complex behavior, not so easy to do. Yawning, even that is such a common behavior across evolution. Again, it'll get a little tricky. But if you say, can you give me a network, for example, that does breath control, might have a little better understanding of the populations of neurons that produce and regulate breath. So it's highly dependent on the behavior you're interested in, and whether we have a reasonably decent understanding of the network that produces the behavior.
Yeah. So, when you're narrowing down, yes, obviously, maybe you understand this, but we need to understand the broader brain, because you mentioned about the worm, the C. elegans worm. We've done a connectomic project. We know 302 odd neurons. We've done like a fruit fly, and then Google has already done a micro bit of the human brain. And besides the human connectomics, there's other approaches. Brain-computer interfaces, invasive, non-invasive, EEG, fMRI, brain organoids. Where you're taking a single cell, turning it into a brain organoid, and kind of reverse engineering all of that. What's your favorite approach to kind of understand the brain? And is there a language going on? Because, if you see in universe, everything seems to be having a language. The universe, it's made out of 4 fundamental forces, and these atoms, and when they come together, we get this beautiful thing called the universe. And people are trying to probe it, via string theory and kind of understand that. Then there's genomes, we're trying to understand the DNA, and we've kind of mapped up a genome, but then we kind of realize, it's not just the genomes, it's epigenomes also, So is there a fundamental language going on the brain, these neuronal firing, these electric currents, is it saying something? And you think that, through these, is there like a specific approach, or possibly like AI, maybe we'll be able to understand the A, B, C, D of the entire human brain?
I think eventually, we'll have a reasonably good handle on how the networks communicate to produce what is the eventual emergent property of the behavior. Each of us, like that elephant, when all the multiple blind human beings looking at the elephant and saying, here's the tail and here's the ear, and everyone describing their favorite part of the animal, and you really don't understand that it's eventually an entire elephant if you're only looking at the tail. So right now the field is running into some of this challenge, partly because you can study it at multiple levels of organization. So you could say, for example, I am most interested in the channels that eventually produce the currents that allow a neuron to fire. And you can get all the detail you want about channels, but you're at a very molecular structural level. Then you can move to a kind of cellular level, saying, I'm interested in how two neurons talk to each other or a few neurons talk to each other. You can then move up to circuits, where you can say, I'm interested in multiple neurons and circuits talking to each other. And then you can say, I'm actually interested at the organismal level in the behavior and modulating this pharmacologically or circuit wise. Part of the problem is that each jump you lose detail, right? Obviously. But you get more and more of the emergent property. But the detail is lost because there's n number of ways to slice this problem and solve it. And there's where the big challenge comes, because each of us is in our own silos, figuring out the details that make us most comfortable, but struggling to be able to talk across these levels. And that's true. Let's say someone who's interested in doing fMRI and wants to look at functional imaging of which parts of the brain light up when an individual is doing a particular task. Now you lose detail of which neurons are active. Are they excitatory neurons or inhibitory neurons? What is the detail of the exact vocabulary in that circuit? But once you get that, you lose the detail of the whole. So this is where the challenge comes. I still think we have a ways to go in being able to, if someone can help us jump across those levels. And it's not that people aren't trying. People are able to jump across a few levels, but to be able to integrate across all these levels, from the very molecular to the output level at an organismal behavioral level, is a hard ask. It's a really hard ask. It's a meaty problem. It's not one that's going to get solved just like this. But we are so much further than where we were, like let's say 10, 15 years ago. And the way tools emerge, and the way we will be able to look at larger scale recordings from multiple networks simultaneously, with things like ECOG in human, with the possibility of neuropixels and next generation CMOS probes that allow you to look at it on scale in rodent. I'm not a pessimist. I'm very much an optimist who says that you're going to see leaps of understanding being crossed.
That sounds so very cool. I really hope that we move away from the siloed approach, because like you pointed out, I think the world works in a way where everybody, or the way they work is so very siloed. And here we are asking one of the world's biggest question, how does the brain work? If we are able to understand, how does it work, if we are able to reverse engineer that, voila, we've got, we will be able to build, the general purpose machine that, the whole vision or dream is. And also, those neurological disorders, there's millions of people who are suffering with neurological disorders. And that happens to be your expertise also. And today, I kind of Googled, what's the numbers, when it comes to neurological disorders. And I was really, really surprised. The numbers is 1 billion.
It's going to go up because as we have an aging population, which we inevitably are going to get everywhere in the world, including India, the numbers are only going to rise, because some of these disorders we didn't really grapple with originally because people had shorter lifespans. Lifespans were generally truncated because of infectious disease, because of other issues. But when you have a longer lifespan, then you're going to see the emergence of a battery of neurodegenerative conditions, which are not small and major to tackle. But coming back to your point about the silos, while I agree that crosstalk across silos is vital, I still think that there's value to domain expertise at each of those levels as well. And so there is room for people who will populate at one particular level and really understand that well. What you want is those people talking to each other more. Because you also need the domain expertise. You need the people who understand individual channel properties, because those are the guys who might probably come up with a, blockbuster drug to treat epilepsy. But you also need them talking to the clinicians and the preclinical people who understand the disease states and the models. So you're going to need people coming together at all levels of biological organization. That's a challenge, but you still need the domain experts.
So I do understand that domain expertise is really, really needed, but I so very feel that if you're thinking about like a broader good for the society, we are at the cusp of that point of time where the world is asking for collaboration. Because through collaboration, I think we can do so much. And the proof of the pudding was the COVID. When the COVID happened, I think a vaccine which takes an 8 or 10 year horizon happened in 6 months. That happened because of collaboration. And just look at the larger good of it. I mean, we can touch so many lives. Like we just said, billions of people suffering with mental health, and you said progressively is just gonna get worse. So maybe if for my audience, it'll be great if you could maybe explain these mental health, why does it happen, what are the causes, depression, PTSD, schizophrenia, what can be done?
The broad term of mental health disorders or neuropsychiatric conditions includes a variety of different disorders under that catch-all phrase of mental health slash. And while the larger numbers are for disorders like anxiety and depression, there's also disorders with a stronger genetic component, which includes schizophrenia and bipolar disorder, as well as obsessive compulsive disorder, and substance abuse, which is a major mental health concern as well. And in many cases, substance abuse is self-medicating to treat other conditions, in some sense. So that catch-all broad phrase, our understanding of what causes these disorders and what drives, the disease condition into a worsening state is reasonable, but has been reverse engineered in a sense. I'll tell you how. We discovered the drugs without knowing how the drugs work. Right? So serendipity plays a huge role here, in that you find out drugs that improve mood states. So you have drugs which are anxiolytics whose origins come from being sleeping pills. Right? So they started with barbiturates and benzodiazepines, which then eventually gave birth to the current generation of anxiolytic drugs that treat anxiety disorders. Then you have the SSRIs, but the origins of the SSRIs are tricyclics, and those drugs were discovered when there was an attempt to try to find better treatments for tuberculosis. And in the process of synthesizing those molecules, you also found that they have effects on mood. It happened to be given during World War II to veterans who were coming out of war and actually had depressive symptoms as a consequence of that life history. In the process, you were trying to treat their tuberculosis, but you also ended up treating you may not even have treated the tuberculosis, but you improved their mood symptoms. So much of this is serendipitous understanding. And you have to think about this as the 50s and 60s. So the 1950s and the 1960s when these drugs come up. Now we have to reverse understand what the drug works on. So you say, okay, this drug is helping a patient. What is the drug actually doing? So you have these drugs that have shown up, but you don't really understand their primary targets. You find their primary targets and they have a decent understanding what the primary targets are, but they only give you half the picture. Because most drugs are slow working, especially the antidepressants are very slow working. They take 3 to 6 weeks to work, and they work only on 2/3 of the population. A third of the population doesn't even respond to most available antidepressants. So you have another challenge, which is a treatment-resistant population. And because they're slow working, you realize that it's unlikely to be their primary target, which is the serotonin transporters or the norepinephrine transporters that are fully responsible for the therapeutic effect. It's likely to be some adaptive change that happens when these drugs are given chronically. That's responsible for the eventual. So you, across the 50s, 60s, 70s, and 80s, you're tweaking these drugs and getting second generation and third generation drugs. You're doing better and better at handling the side effects, but you're not necessarily designing a much better drug, which is still slow working And it still takes, so for example, a drug like Prozac, which is a blockbuster drug for Eli Lilly and made them a lot of money and has been used world over and has been life-saving for many individuals who have severe depression and are suicidal. But is it a great drug? Well, it's a good drug for treatment, but it really is not the best possible drug out there because it's so slow acting and there are individuals who don't respond to it. So we are still, while we are away from the dark ages of psychiatry, we are not in the golden age of psychiatry either, right? We have still not found molecules that can have promise where we have the ability to treat it with a reasonable guarantee of saying it will work and it will work in the next 2 days. So imagine for a psychiatrist today, right? A patient walks in. They can diagnose them. So the diagnostic ability to be able to diagnose them is still descriptive, but it's reasonably decent. So you diagnose a patient with depression. Then you have to use your best possible educated guess to say, knowing my prior understanding of patients and this individual, I think this is the drug I'm going to give him from my, basket of available antidepressants. And then you have to cross your fingers. Then you have to cross your fingers and say, I hope it works. And then you have to send this person who may potentially be suicidal home to say, take this drug and hopefully 2 to 3 weeks later, you're going to feel better. Now that individual has to comply because it's unlikely that they're going to feel better in the next few days. It's going to take weeks. They may not even want to take the drug anymore. They stop complying with the treatment regimen. This is not a good situation. So, but this is what is available in the arsenal to psychiatrists. I mean, they're combining it with cognitive behavior therapy, and no question, behavior therapy is a critical component of the treatment package. But most psychiatrists, because we have something like only 9,000 to 10,000 psychiatrists in our country, that itself is a frightening number considering our population. So we have a real problem and we don't have good treatments that are ones where, if somebody has a headache and you give them a paracetamol, you know that there's a very good chance that paracetamol is going to treat the headache symptoms immediately. Even symptomatic relief is a problem currently for someone who has, clinical depression because it's so slow acting. This is not to say that the drugs don't work. They work, but they work eventually. So we have a serious problem in mental health in terms of the quality and caliber of treatment that is available to a psychiatrist in their arsenal. So there is this burning need for better treatment and a better understanding of what causes the disease and what will help symptomatically and also potentially curatively. Curative we don't even have. We don't have anything genuinely curative. We have symptomatic handling of the situation so that hopefully the person gets better by managing those symptoms. So yeah, we are a far state away. I mean, like the revolution that has happened in cancer, where there are, lifespans are better. Cancer has become a chronic disease for many, where you manage the disease, you manage it as best as you can. It's not the same state in psychiatry. There are still real issues with good quality treatments.
I really hope that the world kind of changes. You spoke about cancer, and then I was watching this podcast, with Joe Rogan and Mel Gibson. And Mel Gibson was mentioning about how he knows a couple of friends, who are using ivermectin. So yes, there are things we are just, maybe understanding more, and possibly we'll go from this, maybe treatment to actually finding cure. Because, if you also look at the healthcare industry, largely it's been such that they are treating the patients, because it's for the betterment of the business, betterment for, making more money, rather than, because cure is never the agenda, because as soon as you kind of get the cure, then the business gets kaput. So yes, so I really hope that, we transition from this capitalistic mindset that we are in currently to actually doing good. And I think, more and more people are asking questions, because I think, these regular media doesn't even, give you these kind of information, So I really hope that.
The problem is the ability to, there's no question that people have sometimes lost faith in the treatment regimes that are available, partly because there's the concern that big pharma is out to push their drugs, right? But the problem with lack of validation of alternative approaches is that And I don't blame patients who want to take whatever is available to them which helps them. So that is totally understandable, right? From a perspective of a patient, there's like, if I feel better on this, I will take it. And that makes sense. But the problem is that there's also equally a push to deny evidence-based science, and at the same time, want to seek out something which is like, for example, the ivermectin data is all over the place, right? There's no clarity whether we have real robustness of things. Need to be tested before they end up straight with the public. Now, the danger with moving too fast, and this is not to say that there isn't merit in some of those alternative approaches and therapies, but they have to be tested. Like drugs go through double blind trials. There's placebo control. You need to test them to determine the veracity of it. Now, there's no question that, for example, exercise is one of the most effective antidepressants at the milder end of the treatment regime, right? No question about it. But it's not something you can market and sell. And so there is no push sometimes to indicate that. And yet there is no question from all the preclinical data as well as the clinical data that voluntary exercise is one of the biggest boosters of a variety of factors in the body and the brain that actually improve mood related behavior. So, should that not be on a prescription list? It should 100% be on a prescription list as a lifestyle alteration to support any other pharmacological intervention. Much the same way, there's equal evidence to indicate that cognitive behavior therapy or behavior therapy is very protective and is vital in the treatment regime. But those are not pushed by big pharma because they're not, sometimes they're not marketable in that sense. And yet they should be part of the prescription regime for sure, right? Because the preclinical and clinical evidence for these are very, very, very good. So what ends up happening is sometimes patients lose faith in that. They are a little worried that, are you telling me something because you think you should be pushing something? Or so this is a dangerous place, because you don't want to lose patient trust in their doctor. And when that starts collapsing and you lose, faith in the broader biomedical science community, then you will go to anything and everything, sometimes which may actually cause you greater harm and might actually derail the entire treatment process. So that is not a good thing. And that, I think, requires, in a sense, very often it requires patient support groups that are actively pushing to ensure that patient interests are looked after, that is the primary person who's seeking treatment, and their interests need to be protected against, commercial interests or other interests. So I think there is going to be a need for that space to be well populated with reasonable people, so that, you continuously push the system to do better as well.
Completely W, but we are in a catch-22 situation of sorts, because yes, evidence-based science is the way to go. Period. Yeah, I mean, there's no other approach. Evidence-based science is the way to go. But we live in a capitalistic world, and what has happened is, if you look at things, deeply in a nuanced way, every institution has been corrupted, be it the healthcare, be it the education, everything is corrupted. So as a layperson, somebody who has a problem and he's going to a healthcare, a hospital, or a doctor for help, what he gets is like, for the price that he's paying, a substandard doctor, or he's got to be a millionaire. So where is the equality over there? These things like education, healthcare is supposed to be, equal for everyone. But here we are in the capitalistic world. We have kind of completely, it's only the rich people can get great education. It's only the rich people who can get great healthcare. The others, my drivers, my maids, and they can look for themselves. So in that world, people are questioning. Then we need to look at it that, okay, not everything is wrong. So I'm not saying that there is no way you should trust the doctors. But even if you look at the doctors at this point in time, most of the doctors at this point in time in healthcare industry are in partnership with the these pharma industries peddling a specific drug. So it's going more.
It's a serious problem because it's fundamental conflict of interest, right? There's a fundamental conflict of interest, and in some sense, you're saying, you're absolutely right that you've created a privilege barrier which makes it impossible for the average person who's cannot even afford access, right, to reasonable healthcare, which is something that should be a universal right. There's no question about it. But the question is, what is the best way forward? How do we democratize access while at the same time maintaining sure that there's some quality control also at the same time, right? Like it's not an easily solvable problem. And it's interesting, there's a recent series of studies just looking at the mental health space, because that's something I'm more comfortable commenting on, even though I'm a preclinical person and not a clinician by any stretch of imagination. The scale of the problem we will deal with in the mental health space in India is so large that it is better to look at preventive than it is to look at curative. Partly because the ability to even diagnose and treat people on that scale, it's going to be a drop in the ocean because of the scale of the problem that is likely to emerge, right? Which means that you need to go in early. You need to go in early into school environments. You need to go in early into early education environments where you provide an inbuilt element of the best form of therapy, which is that you have counselors in schools, but they have to be trained. If they're not trained, they may create a problem rather than getting rid of a problem, right? And at the same time, maybe building in exercise and good nutrition. These are all buffering things that prevent the emergence of mental health disorders, or at least slow down or act as important environmental factors that can actually offset any genetic risk, right? Because there's a genetic component, there's an environmental component, and they're in continuous crosstalk to determine whether someone will eventually develop a psychiatric disorder or not. But at a public policy level and at a public health level, actually everyone is a stakeholder. Every individual who is a government, you know, funding the government in terms of paying their taxes is a stakeholder. People who are not funding and are below the tax limit, whatever cutoff, are also absolute stakeholders. Everyone is a stakeholder. So, how do you, in your own capacity as a stakeholder, start promoting environmental conditions that at least offset that? Like, for example, an educationist who's a teacher. How do you create those environments in classrooms, especially early classrooms in the first decade of life, where a lot of inherent risk is built for diseases that emerge decades later? But that risk is actually set up in that first 15 years. So if you don't get that first 15 years right, you're actually setting up a situation where the disease may come in the 20s or 30s, but you're actually creating the conditions for it to emerge later. So there's a room there for everybody, to kind of play a role, including people in their own families, looking at, parenting / looking at those relationship dynamics that also create ripe conditions to eventually have mental health diseases later in life.
So very valid points, and yes, I think, we living in such a pressure cooker world, I mean, today, I think, the social media has created more harm. Though, I mean, I think that, it's created, I mean, it's a world where everybody can become a friend, but there is so much harm, these Facebook and all, they're manipulating your data, they are hoarding your data, and this digital overload. I mean, we've come to a point and we don't really know how to funnel things which really works for us, It's like an information overload, and there is so much of suicides and things like that. I hope that, we really look into this problem. What you mentioned really hit me, that there's somewhere around 8 or 10,000 psychiatrists in India, and this problem is growing, and if we don't look at it now, I'm sure this is going to be a huge problem. Now you are somebody who's using psychedelics. Now psychedelics is something which is being used through India's history. The Rishi Munis used to use it for enlightenment. Lord Shiva kind of used it.
Did not use the classical serotonergic psychedelics. While India has a traditional history with molecules that are from the cannabinoid family, the serotonergic psychedelics strangely have not been part of traditional Indian medicine. While Somras is referred to and is thought to be one of those psychedelic-like molecules, we actually don't know the plants that are in that, and that's more a mythological structure than it is a thing where you can say this plant and this plant in this combination, these are the molecules. Cannabinoids have been used in India and extensively used in India, both from a medicinal perspective as well as from a traditional, sort of cultural practice. So those have been used. But weirdly enough, psychedelics or serotonergic psychedelics don't show up in the Indian traditional medicinal lore as much as they do in, for example, North Africa, the Amazonian tribes extensively, Central America, as well as some parts of North America where there's extensive usage. There's reports of usage also in sort of Mediterranean and European cultures. We somehow don't have serotonergic psychedelics on our list as much.
I've heard people using these ayahuasca, to kind of, do like a self discovery of sorts. And also, kind of, you get to see the Mother Earth because it seems all of them have the same kind of experiences. Then it seems there's this DMT. 3 years back, they kind of did this, but I just recently kind of figured this out that people under the experience of DMT, if you're shooting laser lights, you can actually start seeing code in the real world. So I'm somebody who's vested in XR deeply. I'm vested in virtual reality. So that kind of stuck me, and like what I mean is everything.
A lot of visual hallucinations on some of these serotonergic psychedelics. And so, because imagery gets fundamentally distorted and fractal like patterns have been reported by individuals emerging because they are under the influence of these molecules, which have an impact on visual imagery substantially. And so, there can be visual hallucinations or distortion of existent images. So, there is that element. Ayahuasca has been used traditionally for thousands of years. So, there's a long history of usage. And, the peyote cactus, which was used by the Incan civilization, the Mayan civilization, and that has mescaline as the active ingredient. So there are molecules, scopolamine, which is a molecule that has also been part of traditional lore. So these molecules have been used for thousands of years, and lots of indigenous cultures use them with sort of a very reverential approach to these molecules, in the view that they altered states of consciousness. And so individuals had to go through purification practices, and this was done under sort of the controlled supervision of a shaman or a witch doctor, etc. So there is a traditional practice. Sort of modern Western science, I shouldn't even say modern, more Western science, discovered these when Arthur Heffter first isolated mescaline from the peyote cactus. Okay, so the first drug ban is something like 1620. So this happens when the Spanish inquisitors end up in Mexico, and they ban the use of peyote in traditional ceremonies because they viewed that as heretical and sort of an opposition to the church, right? So that might actually be the first known substance abuse ban, which is that the peyote cactus was banned, even though it went on underground and, people in traditional practitioners were still using it. Then in sort of early 1900s, mescaline is isolated. And then after that, that's still a natural product isolated from the peyote cactus. And in 1938, Albert Hofmann synthesizes LSD. While he's trying to synthesize something that regulates, sort of completely something different, he ends up making LSD and he leaves it on his shelf till 1943. And then for whatever reason, he takes it himself and then ends up having a major psychedelic trip, which he writes about and reports. And that's the first experience of a lysergic acid diethylamide and LSD ending up then actually being used quite extensively preclinically and in a few clinical trials to try to understand what it does. But this is followed by a period of laissez-faire usage where the respect for the power of this molecule, and it is a very potent molecule, is lost. And this is the period with Timothy Leary, etc. And then you actually end up with a substance abuse ban. So in 1970, all these drugs are put behind like narcotics clearance. They're all Schedule 1 drugs. And so it not just shuts down, I mean, obviously it's meant to ban people from using it recreationally because there were episodes that were genuinely concerning and people using it irresponsibly, etc. But at the same time, you also stop all preclinical research, and clinical research comes to a grinding halt. There are pockets in which it continues, like it continued at Hopkins. There were few places where Rick Strassman did experiments. There was work done at the Center for Psychedelics Research in Johns Hopkins. So Hopkins remains still one of the places where the work continues. But otherwise, it almost comes to a grinding stop. And then you have the resurgence of interest that comes when it is given to patients who have end-of-life anxiety or depression associated with a terminal diagnosis of cancer, where obviously associated with literally a death sentence and no possible treatment, individuals had severe end-of-life anxiety, and to treat that, they were allowed in a clinical trial to give MDMA. And that treatment is then eventually given breakthrough status because it really helped with end of life anxiety. And that is thought to be in some parts associated with some of the mystical experiences people report under the influence of the drugs, and also some of the ego dissolution effects that are reported under the influence of these drugs. So these drugs are very interesting molecules and have very interesting behavioral effects that they exert on individuals. But one has to remember that they are psychotomimetic drugs because they evoke psychedelic states, but they also produce hallucinations, auditory, visual, somatosensory. Now, those are the kinds of states that can actually happen in an individual who has schizophrenia, where there are also hallucinations. So the power of these drugs is that one has to be aware that it is a bit of a double-edged sword, right? Like while they are having these beneficial effects on anxiety and depression, they can also have these psychotomimetic effects. And an individual who has a genetic risk for either schizophrenia or bipolar disorder would be at a higher risk of a psychotic break under the influence of these drugs. Now, what has happened since those original papers that came out about a decade ago or so is that in the last decade, there has been a reopening and a renewal of interest in these molecules because we really, like I said, we don't have great drugs. We need to look at the drugs carefully before we dismiss them as, not, only problematic. But at the same time, they need a careful, concerted, systematic addressal because they are potent molecules and nothing that potent comes without its own risks, right? So there's been a resurgence of preclinical interest as well as ongoing clinical trials. And in India, I think I might be in the minority of literally one or two. I don't think there are too many people in the country who work preclinically on psychedelics. And while we do have psychiatrists who prescribe ketamine at NIMHANS when appropriate if you have treatment-resistant depression, we don't have any clinical trials going on in India currently with psychedelics, and we should have our own clinical trials. We should have our own experts weighing in on it. We cannot just import things after all the work is done in the West because we have a local context, and these drugs work in the context of a set and a setting. And without doing the clinical trials in India, we will not understand the full spectrum of the appropriateness of their use as well as their adverse reactions, which are equally important for us to understand. And the risk is then patients will find ways to self-medicate, but out of the framework of the legally appropriate way of accessing the drugs. And then you have all kinds of ab reactions possible because you don't even know what people are taking, right? I'm a preclinical researcher and I work on these molecules in rats and mice. And I'm very interested in what do they do to the brain? How do they impact it at a molecular and cellular level, but also at the circuit level and influence behavior, and to try to bridge those gaps to the best of our ability. But they are very, very potent and important drugs. And I think we could borrow from the indigenous usage, the respect that they give these molecules. They treated them almost like sacrament. And there's something that we as a community of preclinical and clinical researchers who come from modern medicine training should learn. It's that degree of respect when one is dealing with molecules as potent as this, so that one actually carefully looks at the context in which one has responsible usage, where appropriate, to get the best health outcomes that are possible for people who might need them,
Completely I think over the years these we have maybe over abused these substances, but yes, I think there is something really interesting going on with these molecules which I mentioned about the DMT, that that you flash a laser, and through this laser you can actually start seeing code in the real world. And now this is not just one person experiencing it, it's everybody kind of has that kind of a similar experience. So it's like almost everybody is having the similar kind of experiences. Now, will be great if you could share your lab's work in separating this healing effect from this hallucination, that you spoke about.
One of the papers we recently published, which is a collaboration between my lab leading it and also collaborators at Cornell and Columbia, what we were interested in asking was, even when you give rats a psychedelic like DOI, the one we use in our lab is a molecule called DOI, which was synthesized by Sasha Shulgin, Alexander Shulgin in the 80s. And this molecule is a substituted amphetamine. It's a very potent serotonergic psychedelic, and it works on the serotonin 2A receptor in the brain. We know it produces hallucinations because, of course, from an N of 1, because Sasha Shulgin took it himself. So the only human who has reported that is him, but he knows that he reported it gives very strong, psychedelic and hallucinatory-like states. In rats, it produces a behavior which is a hallmark of hallucinations called the head twitch response, which is produced by all psychedelics. And so it produces that, but it also reduces anxiety. And we were interested in asking, and there's a debate in the field as to whether you need the hallucinatory effects to also get the therapeutic effects. Right? Is it that they're working on that the hallucinatory states are actually important to eventually get the therapeutic effects? And many psychiatrists would tell you that they believe they are. And then there are some individuals who say, no, these are separatable. And if they are separatable, in principle, you should be able to design drugs which are inspired by psychedelics, but don't give you the psychedelic trip, but simply give you the therapeutic effects. So this is an area of hot debate, and there is no resolution for it at the moment. What we wanted to ask in our rats was, which part of the brain is responsible for this reduction in anxiety? Okay. And the way we study reduction in anxiety, we do a behavioral task. It's an elevated plus maze. So it's like a plus, and it's raised 2 feet off the ground. And there are 2 arms that have high walls that are, obviously rats like to hang out in dark, closed spaces with big walls. They don't like to come out into the open. And there are 2 open arms that are brightly lit and 2 feet off the ground. So obviously, when you just take a regular rat, which has not been treated with anything, it'll spend most of its time in those dark arms. Maybe it'll come out and check out the open arm for a little bit, but it tends to run back quickly into the closed arms. So when we give rats psychedelics, they spend a lot more time in it's a huge effect. They go into the open arms. They like hanging out into the open arms. They don't seem to be scared of that open arm space. They're exploring it. They're looking over the edge. They walk up and down the entire open arm. So this is a proxy behavior to see a reduction in anxiety in the animal. Now we know it's a anxiety-like behavior because all the drugs that treat anxiety in humans also have similar effects in this particular animal model. Okay, so psychedelics do this. Now, we know this. This is not some new discovery. This has been known since the 70s and 80s. Actually, since the 80s for DOI. But we don't know where in the brain it works. So that part is like a black box. We have this brain, but we don't know where this effect is happening. So a very talented former graduate student of mine, Prachi Tiwari, who's now at Hopkins and continues to do work on psychedelics. When she was a PhD student in my lab, she decided to identify which part of the brain produces this behavior. So she did surgeries where she cannulated the brain and delivered the drug only to that part of the brain, not to the whole animal, right? So when she did that, she went to something like 7 different brain regions, and she narrowed it down to a structure called the ventral hippocampus. Okay. Now, that was a bit surprising because the ventral hippocampus is not a part of the brain where there is a lot of receptor for the drug to work on. We would have predicted the cortex or the prefrontal cortex where there is an abundant amount of receptor. So this itself was a surprise that it turned out to be a brain region which doesn't have very high levels of the receptor. But Prachi was able to show that it's that part of the brain. And then into that same part of the brain, she put in a drug that blocks the receptor and gave the drug to the whole animal. So the drug can now go everywhere in the body and the brain, but it cannot work on the receptor in this ventral hippocampus. And when she does that, the drug has no effect on anxiety. So already you're able to narrow down from this black box. So in a sense, think about it like mapping this. You have a black box that's the whole brain. You now know it's the ventral hippocampus. But the ventral hippocampus has 1 million+ neurons. So now the next question is to narrow it down to which kind of neuron in this part of the brain. And here we were helped by a very talented graduate MD PhD student at Cornell called Pasha Davudian in Alex Kwan's lab. He implanted electrodes and recorded from the neurons in this part of the brain and narrowed it down to a type of inhibitory interneuron called a paravalbumin interneuron. Okay, so it's basically like, in a sense, how best analogy I can come up with is, imagine India is the brain. You give India the psychedelic, you get this reduction in anxiety. You have narrowed it down to Mumbai. Mumbai is the ventral hippocampus. You expected it to be Delhi because it's a capital and that's where a lot of the power is. That's where the 5-HT2A receptor is in my analogy. Turns out it's Mumbai. Now in Mumbai, you need to figure out which suburb. Okay, so you're trying to figure out which suburb. So figure out that it's Churchgate. Okay, so now within Churchgate, so it's an interneuron. It's some inhibitory fast spiking interneuron. Now, which buildings or which parts of Churchgate, right? So narrowing it down bit by bit, we figure out it's these parvalbumin neurons. Now, if this whole hypothesis is true, we should be able to go in and manipulate just those neurons without the psychedelic and produce the same effect, right? If we are true in our hypothesis. So we go in and we actually activate those parvalbumin neurons. And when we do that, we reduce anxiety. And when we inhibit those parvalbumin neurons, we actually increase anxiety. So this is what Prachi was able to show. That manipulating just that subpopulation of neurons in this part of the brain is enough to actually manipulate anxiety-like behavior. And the last thing she did, which was a really nice experiment, was she took an animal where there's no 5-HT2A receptor at all. You've knocked out the receptor. So there is no receptor for the drug to work on. And sure enough, as expected, in this knockout mouse that doesn't have the receptor, the drug doesn't work. It doesn't give you any effect on anxiety. Then she put back the receptor on these parvalbumin neurons and showed that if you replace it back only on the subpopulation of neurons, it's enough to get the behavior back. Right? So it allows you to go from this black box to now mapping down which class of neurons is being targeted. Now, I told you all this. This is not the part of the brain that produces the head twitch behavior or the hallucinogenic behavior. So already you have separated these two. You know this is a different part of the brain from the part that's producing the hallucinations. Why does this become interesting? It becomes interesting because there is a pool of people who are now just combinatorially generating drugs inspired by the psychedelic backbone. So you know the drugs that exist, both naturally and those that are synthetic. You can modify it using combinatorial chemistry and come up with a library of molecules that are structurally slightly different. Some of them are psychedelic-like, but don't produce the hallucinations or the psychedelic experience. Do they produce the therapeutic effects? In which case, we may come up with a new sort of drug. And there are many people in the world who are doing precisely that, looking at ways to tweak these molecules to come up with a better drug that might have a fast effect. Because one of the powerful things that these effects are fast and they are long lasting, which is unusual, right? We don't have a drug in our arsenal, perhaps other than ketamine, that falls into that category, that is fast acting and long lasting.
Kudos to you, your PhD student, and I think putting all of these together, it's so exciting that we are now trying to probe and understand, maybe like go neuron level, and get something out, So I really wish that there's more interventions, so that we can find not just treatment but proper possible cure. Now your recent work on mitochondria in neuropsychiatric disorder is very, very cool. Could you explain in simple terms how something as fundamental as cellular energy production can go bad and contribute to depression and anxiety?
Yeah. So there's been for a long time so mitochondria are like the bacteria that our metazoan cells engulfed, and that became our powerhouse. Everybody knows it as the powerhouse of the cell, right? It's the organelle that generates your energy currency, which is ATP. That's what you burn. So in a sense, you can think about it as your electric station that gives you the electricity to run the lights in your house, right? If that fails, you have a power shutdown. You can't do much. You can't do anything in the dark, right? So in a sense, what we stumbled on was super interesting. It was already known for a long time that mitochondrial dysfunction may be a component of what is going haywire in mental health disorders. There's already been a body of evidence. We stumbled on this finding purely serendipitously. Actually, the story is quite interesting. A former postdoctoral fellow in my lab, Sashena Fanibanda, was working on a project which was funded actually by a FMCG, a large FMCG, that was interested in looking at food-derived nutritional substances that are protective to the brain. So they gave us a laundry list of things. They said, why don't you test this? And we're like, okay, we test it. So we put it on our neurons and we were looking for things that would improve neuronal health and boost and improve mitochondrial function. And all we did was kill the neurons. Okay, many of the things that they asked us to test, we managed to just kill the neurons. So at some point, I remember sitting with Sashena and telling her, listen, we better show something that makes the neurons healthy, because otherwise they're going to think that all we know is how to kill neurons, because every molecule they were interested in was only just killing the neuron. So that was not a good thing. And so we were looking for a positive control, something that would be a big booster. And obviously the natural thing is a growth factor. It was well reported. So we took a growth factor, and as expected, we got an increase in neuronal health and boosting of mitochondria. But my lab is interested in serotonin, has been interested in serotonin forever, right? So she was just playing around and she said, I'm going to put some serotonin. So she just decided to put serotonin on the neurons and ended up boosting mitochondrial numbers and mitochondrial function, which she found really hard to believe. So she came to me and said, forget the result we were trying to go after and what we were trying to show, but I think I've stumbled on something which is 10 times more interesting. So both of us, we are like, no, maybe this is not real. How has everybody missed this? Like this should have been like found earlier, right? Like how did this get missed? So she did the experiment again. We looked at the data again and we just couldn't believe it. And then we started seeing, it's interesting, right? How when you start chasing a problem, then you find things about the problem. Otherwise, you don't read about it. So I read this very interesting paper by a person called Professor Vidita, who used to be, a serotonin researcher of some repute. He had written a very provocative review article on serotonin, sunlight, and suicide. And the combined title, which kind of just didn't make sense to me. And I was like, what is he talking about? Turns out serotonin as a molecule is 3 billion years old. 3 billion years ago, there were nothing had neurons. It was the early stages of evolution, and there is no neuron, there's no organism that is a neuron. Okay. Animals, as we understand them with nervous systems, show up something like 750 million years ago. So nervous systems have not even evolved, but serotonin is already in place. In the very earliest stages of like algae and plant evolution. And it turns out that when you actually have to trap light and convert light energy into food, which is the first thing that you have to do for life to exist on this planet, you have to get light trapped. Now, to trap light, you need a molecule. And the molecule that was often used was tryptophan, which is an amino acid that absorbs light, and it's part of the sort of chlorophyll complex. So it's allowing you to trap light and convert that eventually into glucose. That's the first thing that you learn in photosynthesis, textbook level photosynthesis, right? Now that glucose you make is going to be burnt like a combustion engine will be burnt to give you ATP eventually. And, so you're using oxygen to burn the glucose and give you energy. And that's what mitochondria are doing. Now, in the process, as a side effect, you produce free radicals. Can't help it. It's just a natural side effect of this. So these are all these molecules that have these charges. So, superoxide radicals, hydroxyl radicals, they're going to go and bang against your proteins and bang against other molecules and cause damage. They're going to, there's going to be lipid peroxidation. There's going to be there's all kinds of things that are happening which you don't want, which means that to prevent that from happening, you have to co-evolve an antioxidant, something that's going to scavenge all this garbage up, right? Guess which molecule may have been one of the evolutionarily old antioxidants? Serotonin. Serotonin is derived from tryptophan. It's a derivative of tryptophan. It's just 5-hydroxytryptamine. That's its structure. So it turns out that it's an ancient antioxidant molecule. It's been around forever, long before there were brains, long before there were neurons, long before it became a neurotransmitter, long before it regulated mood and behavior. So this was really interesting to us. And so we started wondering, do you think we've stumbled on something which is just an evolutionarily old process? Something that's actually then been hijacked and used in neurons to protect neurons and, to boost mitochondria, boost function, simultaneously scavenge free radicals. And bottom line, what Sachena was able to show very nicely was that serotonin in cortical neurons through the serotonin 2A receptor sets up a cascade that boosts the number of mitochondria and boosts their efficiency. And this is important in the neuroprotective effects of serotonin in neurons. So turns out it's also the serotonin 2A receptors. And guess what? Psychedelics do the same. Psychedelics are also potent boosters of mitochondria. So this is now like convergence coming from different places, that mitochondria may actually be boosted not only in their numbers, but also in their efficiency in protecting neurons. Yeah, we stumbled on this. I wish I could say we had some very grand hypothesis, but very often interesting discoveries happen by pure fluke.
Accidents accidents. Yeah, but how cool is that? Now, is any of your work in your lab being translated into medicine? Is anybody looking into that? And will be great because there'll be like families who kind of listening who are suffering, with the depression or stress, anxiety, or schizophrenia. It would also be great if you could, maybe give a set of, maybe clinically, approved drugs, with which people can kind of look into.
Currently, I mean, so I work closely with collaborators at NIMHANS who are clinicians who are actually working directly with patients or working with patient derived induced pluripotent stem cells. So, what we see in rats and mice, we can translate in collaboration to asking whether human neurons respond the same way. And the first set of preliminary findings that we have clearly indicate that biology is parsimonious, which is what we already know, that it uses the same logical structure over and over again. So, what we see in mice, what we see in rats, we also see in human neurons. So, there is a similarity, right? So, that we can clearly see. So, in that sense, we're able to translate the findings to human neurons. That's still one step away from the human being and directly moving into the clinic. What I have been asking my NIMHANS colleagues to do is to push for structural reform at a policy level in the country, which will allow India to have their own clinical trials. And NIMHANS is probably the best space to lead it. I'm a preclinical, I'm a PhD, I'm not an MD. So this is not my wheelhouse or expertise, but I would love to see that happen at NIMHANS where a good clinical trial, well controlled, well managed, is run so we can see what in our context is the therapeutic usage. I think ketamine for treatment resistant depression is already in use clinically. But I think psychedelics are important molecules for us to test in the Indian context. I mean, every other country has a policy and ours is moving forward. We can't be caught sort of napping on this and then wait to catch up because, we missed the boat in a sense. So I hope that the clinical colleagues and collaborators will drive this. The other angle that I think has potential real clinical translation is work that was funded by the Padmavati Venkateshwara Foundation. It's a very interesting story. So, the Padmavati Venkateshwara Foundation was started by two doctors based out of Andhra Pradesh who are donating their entire personal wealth to science. It's a rather remarkable foundation, and they do really remarkable work. And I was very lucky to get their the first grant that was given by the PVF Foundation. I received along with a very talented postdoctoral fellow in my lab, Prateek Chaudhary. So, what we were interested in asking was about early risk and early stress. How does it set you up for risk for psychiatric disease from a preventive point of view and a public health preventive point of view? And one of the things we were working on was the fact that early stress speeds up the entire aging process. So, what should normally happen as you age is now happening way earlier in middle aged life. Okay. And we were looking at many markers that are indicative of this. And this was done in rats, but we are now translating this to humans where we have samples from individuals who have a history of early stress, and we are actually looking at what happens in their serum samples itself. But what was the mandate we got from the Padmavati Venkateshwara Foundation from Dr. Sudha and Dr. Nageshwara Rao was, please take an over-the-counter nutritional supplement as a potential intervention rather than a drug, because we are interested in things that can be scaled, that can have public health impact. And the molecule we went with is vitamin B3, not D3, B3. Okay. To see if it can actually prevent or the emergence of some of the conditions that happen with early life stress. And it's called nicotinamide. And we find that it is a very potent protector against the long-term consequences of early stress and early trauma. Now, we believe that that has straight out much more clinical translational promise. And certainly the idea is not ours alone. There are many, many people in the world that work with nicotinamide and are thinking about it as a gerotherapeutic. But in India, given the scale of the early stress we have because of a combination of poverty and adversity and circumstance, we have a very young population. And several of them face serious adversity in early life. Poverty is itself one risk factor. While it can be buffered by other factors of a social support system, it's still a major risk factor. So, given early adversity, are there nutritional supplementation approaches that might offset some of the cost of that early trauma. So this is an area in which I think there is translational promise, and we would be very keen to work with clinicians to do this. But as I said, I'm a preclinical researcher, and this I can only do in collaboration.
Right, right. Shout out to PVA Foundation for helping researchers such as yourself, and there should be more people such as themselves. So your work centers on SIRT1 and mitochondria. These are like the holy grails of the anti-aging field, and human longevity is one field. Like everybody is kind of racing towards that. Because it's like a multi-million dollar industry. So does this work overlap? And it'd be great if you could kind of talk about that.
It does, but I mean, what's so interesting is how much commonsensical stuff there is in the longevity research field. And the number of things one finds out mechanistically, but when one walks back from the mechanism to what was the intervention, one realizes that the interventions are often fairly sensible when it comes to longevity. You didn't need all the rocket science, because some of the insights were so straightforward, like it's exercise. Good exercise is a quality life booster of health span, no question about it. Good sleep, again, another quality booster. Caloric restriction and caloric maintenance and nutritional control is again another modulator. All of these speak to the molecule. So what science gives us is an understanding of the molecular framework that all these things are impinging on. Exercise is also hitting the sirtuins and PGC1 alpha. So is caloric restriction and caloric modulation. So the pathways are common. Whether it be a worm, it be a fly, it be a mouse, a rat, a monkey, or a human, biology tends to use the same building blocks. They add complexity, but the building blocks are similar. In that list of molecules are sirtuins, the mTOR pathway, AMPK, PGC1 alpha, these molecules that show up on many people's lists. They are the same molecules. One can hit them by using drugs. One can also modulate them by changing lifestyle. And lifestyle is an underappreciated, powerful tool to look at longevity and quality of life. Of course, you don't want to just increase lifespan. You want to increase health span. Yeah. So not surprising. I mean, some of the stuff is like, what your grandmother told you, to do certain things, right? Now we have an understanding of why those things work, because we have a good understanding of the molecules, but eventually commonsensical advice has its own role.
In the space of AI, there's companies such as OpenAI, DeepMind. They are trying to build these things called AI agents. And the goal over there is to build AI agents eventually, which would become like maybe scientists, co-scientists. Google has already kind of developed something called as a co-scientist. Sakana AI has kind of developed like a co-scientist. How are you leveraging AI for neuroscience? That's my first question. And second question, obviously, that we spoke in the beginning of the conversation, general purpose machine, that's the holy grail of people kind of, building these large language models, and at this point of time, we clearly, the scaling method of just kind of, throwing in data and expecting that the models could to have like human level intelligence is hitting the wall, and so now people are saying, scaling is definitely not the approach. Somebody who's been invested in neuroscience, what do you think could be that alternate approach to possibly maybe develop, general purpose machines?
Yeah. So one of the things that, of course, there's a fair bit of use of AI in all the automated behavioral monitoring that is happening, because we can manually score only a battery of stuff. And there's a limited battery of stuff that one can. So there's a lot of AI inspired / algorithms / programs that will allow you to analyze large data sets. Now, one of the bottlenecks is the ability to easily do this on scale with all the data that's available, right? Right now, people are individually doing it. So, like a program like Deep Lab Cut, which is freely available, running against, all the mouse lines that exist, all the modulations people have done, where you can do a comparative pull out of the data sets, would be immensely powerful for you to build functional working models of data for behaviors, right? So that's already one place where the ability to do this is within reach, very well within reach. The biggest problem is the data availability, and making it open source enough that you can actually have one space where all this gets analyzed and you can compare across data sets that have come across the world from different labs, etc. So that possibility is huge. I think the other place where This is of course being used extensively, will also be drug design. So if you have scaffolds and you want to predictively look at their ability to modulate signaling, but you can build scaffolds and run this as a in silico experiment until you start narrowing down what you want to actually take as a pipeline to the bench rather than having to do high throughput screening of everything, right? Now that comes with its own advantages, disadvantages, because it depends on the quality of data that you use as a screening tool. But that's getting better and better and better. So given that, I think that can be like a way to cut down time significantly because it helps you narrow down. So let's say I take a scaffold of a molecule and say, I want to build every possible structural variant of this battery of drugs. Every possible structural variant. And I want to bash it against all the serotonin receptors and every other receptor that's out there to see what will be its off-target effects, what are its binding efficiencies, what is the signaling signature it induces. It gives you the whole signaling pattern for those drugs that you are now going to narrow. And then using that information, you make a much more educated choice of what you want to take forward rather than going with one. That's again another game changer. The drug industry, of course, is already capitalizing on this extensively. But I think that will be a game changer going forward. Another element will be the personalized element that comes in, which is right now we have no person. This is all agnostic to variation from individual to individual. We're treating everybody as the same. One big thing, everybody will respond like this, and then all that individual variation is actually not a good thing. We think of noise and we say, oh, no, we don't want it. We want the data to cluster. But the noise is where the information is. The inter-individual variation is where the big stuff is happening, right? Now that we can capitalize on. If one can, for example, get a predictive understanding of how individuals with specific genome information will respond to a battery of available. So imagine a situation where you have a psychiatrist who says, I have this person's genome information. I have the battery of drugs that I, have, and I know what their symptoms are because I have extensively listened to it. If I had a better way, an algorithm other than my own brain, which is taking the best educated guess, to say, if I put this person on this first antidepressant, that I have a X percentage chance that it will work. Rather than playing a guessing game and saying, oh, you go take this, 6 weeks later, we'll see if it's worked. If it's not worked, we'll switch you to a second. If that doesn't work, we'll switch you to a third. If you could compile that data and overlay it on genome information, hasn't happened yet, but is bound to emerge, right? You bring in personalized element, and the personalized is going to be vital because everybody is not the same. And it's not like just because you tested X drug here, it's going to work exactly the same on any individual. So that information, once it starts getting leveraged to build a viable algorithm that you can trust. I mean, you have to test the algorithm and you have to see the veracity of it. But if you have even something available like that, I think it's a game changer.
My last question to you. Libet experiment. Will be great if you could maybe explain to the audience what a Libet experiment is, because Libet experiment says that there's no free will. And then there's Robert Sapolsky, he's written a book called Determined, which says that anything and everything is determined. So maybe will be great if you could maybe share your thoughts on Libet experiment, free will, and your moonshot.
I'm going to skip this free will question only because the most painful question that gets asked to all neurobiologists. And I think Robert Sapolsky, while I have loved many of his books, and Determined is also a fantastic book, I don't know if, I want to tackle that one particularly, partly because we have still poor understanding to be able to mechanistically explain every single behavioral outcome purely from an understanding. We're just limited in our understanding. There's no question that a large number of behaviors are driven by an understanding of what is the interaction between experience and circuits that produces the behavior, right? And we have a decent understanding for several. I think let's wait. I'm one of those people who'd like to just wait, before I want to comment. I think I agree with Sapolsky in large measure for many, many things, but I just want to wait. So I'm going to let that go. But I'm going to take the moonshot experiment question because that is always a lot of fun, right? I think if you had a way to simultaneously look at the interactions of multiple neurons in the brain talking to each other, and that there were tools and technologies which were invasive but minimally so, that allowed us to simultaneously look at the crosstalk between neurons of all kinds of circuits at the same time and then look at the behavior at the same time, it would be a game changer. We are not there yet. So this is my moonshot experiment that some neurobiologist slash technologist is going to design the tool that we need to simultaneously image or record or gain information from all those millions of neurons. I mean, like 100 million, then maybe 80 billion is not such a, fast stretch. Like, be able to look at large numbers of neurons simultaneously and be able to, now there I think AI is going to become vital because we'll drown in data and we will not be able to make sense of it. But the power of that will be transformative to be able to, even in a rodent brain, which is a fraction of the neurons that a human brain has, but still to be able to do that would be immensely powerful.
Thank you, Professor, for taking time and being part of the podcast. Yes, I think we're sitting in exciting point of time. I think there's like a human and machine convergence, which is going to happen in the next few years, where all a science is going to be accelerated because of AI. And I think, people such as yourself, your moonshot, and sounds so very exciting when you say that you're probing, maybe multiple neurons or maybe going to like a single neuron, if we are able to kind of manipulate that, invasively, non-invasively, I think we'll be able to kind of, take away the biggest problem in mankind. We spoke about mental health, almost every 1 in 7% in the world today has some kind of mental health condition. And if we are able to kind of understand our brain, we'll be able to maybe take away all of those mental health issues, right from depression, anxiety, stress, schizophrenia, cerebral palsy, autism, ALS, and so on and so forth. So that's an exciting part. But it's not just that. I think, maybe if we are able to kind of probe deeper and maybe someday be able to kind of really understand the language of the brain, that means we'll be able to reverse engineer the brain. And the day we are able to reverse engineer the brain, maybe that will be the blueprint of how we kind of, build a general purpose machine, and that will be like the birth of maybe like another species will go hand in hand with us and maybe create a better future for us. So really, really appreciate you taking time and being part of the podcast. And to my listeners, if you like what you see in here, then please press the subscribe button. Until next time, see you guys. Bye-bye. Thank you.